Hi, this is Alan Johnston. I'd like to welcome you to AU Virtual, and in particular to our class today on Principles of Hydraulic Analysis for Fire Protection Sprinkler Systems. In today's building information modeling environment, analysis of all parts of a building are more important than they ever were, and fire protection is becoming a bigger and bigger part of that initial design, so that I feel like this is a valuable topic and a timely topic to visit as we go forward in that building information modeling environment. We're going to talk about hydraulic analysis by starting with the hydraulic formulas. And in talking about those formulas, I want to take an empirical approach to explain a little bit of how those formulas could be derived rather than just presenting the formula and say, here, you plug the numbers into it. We'll also talk about the standards and codes that are applied to that design. First, the fire protection standards. And then we'll also mention some of the plumbing standards and a little bit how they compare to each other. A big difference between those is the engineering assumptions that are used in applying those physics that we talk about early in the program. Those assumptions then dictate the actual formulas that are used and how they're used. By doing that, we can make a comparison then between the fire protection analysis of a piping system and the plumbing analysis of a piping system. We'd expect then by the end of the day that you would be able to know and apply those basic equations that are used in the hydraulic analysis. We'll actually spend some time going through the details of the procedures that are used in that hydraulic analysis for sprinkler systems. We'll also be able to identify the appropriate sprinkler design standards so that you know, at least in the basic form, which standards to apply to which designs. We'll also be able to differentiate between the design basis for fire protection and plumbing systems, and as a result be able to recognize when any given piece of software says that it can calculate friction loss through a pipe. That doesn't automatically mean that we can apply it to any kind of analysis. It needs to be pretty well specific for fire protection. And I think in that sense, even though this is by no means a program based on specific software, but rather concepts related to building information modeling, it'll still give you a basis to evaluate various software products to determine their level of integration with that analysis process. So let's start with the basic equations of hydraulic analysis. And those equations, again, I want to present in an empirical development. Those equations are actually three equations: the pressure required at an operating sprinkler, then the pressure it takes to push the water for that sprinkler and all subsequent sprinklers through the system to overcome friction loss, and then finally the pressure required to actually raise the water to whatever level we need it. That first equation we'll study empirically, and let me start by giving you the punchline. The formula itself is Q, that's the flow out of a sprinkler, equals K, that's a constant for the sprinkler orifice itself, times the square root of P, which is the pressure at that orifice. The empirical development can start with an apparatus that I'll spend a few minutes just describing. It's a very simple apparatus. You can see some piping, and you can see some valves, and you can see, or a valve, and you can see some pressure gauges. You can see a flow receptacle and a clock. The beginning of this pipe over on the left side, I'm saying, is connected to a sort of unlimited source of water, a very, very large water tank. And then from the water tank, we've got a fire pump, or a very large pressure and flow capacity pump, so that we can get virtually any pressure at any flow out of that pipe in the upper left-hand corner. The gauge on the left shows that the pressure is whatever we want it to be, a very high pressure showing on that gauge. In various runs of this test, we're going to open this valve. We're going to open it very quickly, and then we're going to shut it very quickly. We're going to leave it open for a minute at a time. And we'll calibrate that valve so that we can open it to get a specific pressure on the outlet pressure gauge. That outlet pressure gauge we can operate at 5 psi, 10 psi, 20 psi, and so forth. Ultimately, we're trying to test the performance of a sprinkler head. So obviously, our apparatus has a sprinkler head in it. And normally, a sprinkler head has a little glass bulb or some strut of some sort that holds the valve shut. For the purposes of our test, we're going to remove that glass bulb, and we have an open orifice. So as soon as we open the valve, water will come out of the sprinkler. As soon as we shut it, water will stop coming out of that sprinkler. And then below the sprinkler is a big tank. A garbage can holds 30 gallons. This is a little bit larger than average garbage can, but has been marked very carefully so that we can show how much water has collected in that during the 1 minute. And the 1 minute will be timed on our clock. So let me run that first test very quickly. I'm going to open the valve so that we get 5 psi. We're going to run water for 1 minute, and then we're going to measure how much water came into the tank. In this particular test, hypothetically, we got 12.5 gallons, and so I'm going to create a chart on which I'm going to represent the 5 psi and the 12.5 gallons. We'll also create a piece of graph paper to graph that result. Actually, we got 2 results in that test because when the valve was shut, as it is now, we had a pressure of 0 and we had a flow of 0 in a minute. So we've got 0 psi at 0 gallons a minute. And then when we ran it for 1 minute at 5 psi, we got 12.5 gallons. So that's 12.5 GPM, gallons per minute. Time to run our second test. And when we do that, we're going to open the valve to get 10 psi. We'll run that for a minute. Water will collect in our garbage can, and we'll get 17.7 gallons, which means 17 gallons a minute, or 17.7 gallons a minute. We'll put that on our chart, and we'll graph that on our graph paper. To speed things up just a little bit, I'll just go ahead and run the next phase of the test at 15 psi. At 15 psi, for a minute, we got 21.7. We'll go ahead and transfer both the 15 psi and the 21.7 to our chart and put that on our graph paper. Each time we reset the tank by emptying it, we reset the clock to 0, and then we're ready for the next segment of the test. Ultimately, then, we've got a chart of various pressures and various flows, and we've got a graph of those pressures and flows. What we'll do next is work with that graph and show how that turns into a formula. Well, very well. We said we'd study that graph and see if we could use a little bit of mathematics to determine a formula for the relationship between the pressure and the flow. Let's get the apparatus out of our way and focus our attention on the graph for just a minute. I'm not as much of a mathematician as my friend Norbert, so I showed this to my friend Norbert and said, Norbert, what do you think about that graph? Does that represent something that would be a formula? And he said, well, that looks like a parabola. And the equation for a parabola usually involves the square root of the one axis compared to the regular power of the other axis. So he suggested that I take a look at the square root of the pressure related to the flow instead of the pressure related to the flow. And if we did that, we'd get rid of the graph that related the square root, the regular pressure to the regular pressure, and focus on the square root. So 0, the square root of 0 is 0. The square root of 5 is 2.2. And so we could start a piece of graph paper that started at 0, 0, and we're recording now on the vertical axis the flow, and on the horizontal axis the square root of the pressure. So I started to say the square root of 5 is 2.2. We could graph 12.5 GPM at 2.2, the square root of the pressure, and then we could take the square root of 10, that's 3.2, and graph that against 17.7 for the flow. 3.9 is the square root of 15 with 21.7. 4.5 is the square root of 20. 5 is the square root of 25, and 5.5 is the square root of 30. So I don't have to be as good of a mathematician as my friend Norbert to look at that and say, gee, that looks like a straight line. And the equation for a straight line, especially one that goes through 0, 0, is a very simple equation. It's just y equals mx, where m is the slope. And we could measure the slope just by saying between 2 and 3, that's a unit of 1 in the horizontal direction. The slope is the rise over the run. And for that, we could take and measure the flow at 2 and read the flow at 3 and find out that that's 12 and 17.6 respectively, or a rise of 5.6. So I said the equation for a straight line is the flow equals the rise over the run, or Q equals 5.6 times the square root of P. That says I don't have to get my garbage can out every time I want to know what the flow is out of a sprinkler at any given pressure. I can simply plug it into this equation. Another way of writing that equation then in a more general sense is that Q equals K square root of P, where K is the constant for the sprinkler is equal to Q divided by square root of P, just rewriting the equation. And if we took each of the experiment results and refigured the K factor, 12.5 over 2.2 is 5.6, 10 over, or 17.7 over 3.2, 5.6. For each one of the results that we got, it's 5.6. Now I got to tell you, for the example here, I kind of made those numbers up and they all came out exactly 5.6. If I had a real pressure gauge, it would be harder to read, and if I had a real garbage can, it'd be harder to read as accurately as I did in this example. Nonetheless, I'd get pretty close to 5.6 5 or 6 times, and that's exactly what the manufacturer does when he tests his sprinkler. And then they take all those about 5.6s and they average them, and then they publish that. We have in this next slide a sample of a manufacturer's technical data sheet showing where they publish that K factor. Rather prominently displayed in the upper right-hand corner of this particular cut sheet is the model number V27 and the K factor 5.6. I've also prepared a list of representative K factors for various manufacturer and model numbers. If we sort of focus on the first 2 manufacturers, you'll see that there's different orifice sizes and that each of the different orifice sizes has its own unique K factor. Those K factors are predominantly affected by the actual diameter or actual internal diameter of the orifice. So the key characteristic of the sprinkler head is that orifice size. You'll see here that for 2 different manufacturers, 7/16 orifice is roughly a 4.0 K factor, and that a 1/2 inch orifice is about a 5.6, 17/32 is 8, 5/8 is 11.2, and for the most part, the orifice size determines the K factor. Let's summarize then. Our calculation of the flow and pressure out of a sprinkler outlet is given by this formula that we derived empirically as Q equals K square root of P. That's very much affected by the sprinkler K factor and indicates that you will not know the pressure at any given sprinkler unless you know the flow, or conversely, you won't know the flow at any given sprinkler unless you know the pressure. By comparison, in a plumbing supply calculation, it's the fixture type that is the significant characteristic in determining the pressure and flow, and the standards prescribe a specific pressure and a specific flow for each fixture type. So a sink would have a fixed number of fixture units, which converts ultimately into a flow, and a required minimum pressure, similar for a toilet or a shower or any other fixture. Therefore, if you know the fixture, then you automatically, by the standard that you're making use of, you know the pressure and you know the flow. That's a key difference between fire protection calculations and plumbing calculations. I think we'll use that to close out our discussion of the pressure required at an operating outlet and move on to talking about the pressure required to overcome friction loss in a section of pipe with water flowing through it. Like before, I'll start with the punchline, which is the formula itself, and then we can talk a little bit about the empirical method that you could use to derive that calculation or that formula. Formula represented here is P sub F, that's the friction loss in PSI required to push a given amount of water through a pipe, is equal to 4.52, which is a constant relating the British units, times the length in feet, times the flow through the pipe to the 1.85, where the flow is represented in gallons per minute, divided by a roughness or a smoothness coefficient of C raised to the 1.85, and divided by the diameter in inches, that's the actual internal diameter of the pipe, raised to the 4.87. And this is known as the Hazen and Williams friction loss formula. I've got just an indication of the apparatus that we would use, shown here to the right. So let's start again with a little bit better description of this apparatus that we'll use for this series of tests to develop empirically the friction loss formula. Apparatus very similar to the one we used for the outlet pressure. It has an unlimited supply. It has an upstream gauge or a supply gauge that shows we have pretty much any amount of pressure we want to use for the rest of our test. And then the single outlet gauge has been replaced by two gauges here. This is the upstream gauge I'll refer to it as, and the downstream gauge I'll refer to it as. And the difference in pressure between those two gauges is the friction loss. We've also replaced the sprinkler head with just an open pipe, and we've kept the container to collect our water in, and we've kept the clock to measure the time with. So when we open the valve at various calibrated amounts, we can create a friction loss and measure the flow. Well, let's run our first test. We're going to open that valve till we get 3 psi at the upstream, 2 psi at the downstream. We'll run it for a minute and find we collect 5 gallons a minute. Again, we'll chart and graph those results. So we put the 3 upstream and the 2 downstream pressures, and we put the flow of 5 gallons a minute. We subtract the 2 pressures and get 1 psi as the friction loss. Then we can graph that. Then we could clear our tank, reset the valve, reset the clock, and run our second test in this series. In this next test, we'll happen to get 6 psi upstream, 2.4 psi downstream. When we run that for a minute, we collected 10 gallons a minute. So we can put the 6 psi upstream on the chart, we can put the 2.4 downstream on the chart, and we put the 10 gallons a minute. And when we subtract the upstream, or the downstream from the upstream, we get 3.6 pounds friction loss. Once again, we can empty the container, reset the clock, and use another calibrated setting on our valve. This time we get 11 pounds upstream, 3.4 pounds downstream. After a minute, we've measured 15 gallons, so we can transfer the upstream and the downstream pressures to our chart. We can transfer the 15 gallons per minute to our chart, subtract the downstream from the upstream, get 7.6 pounds. We'll graph that. And again, like before, I'll skip ahead a little bit, say we could run 3 more tests and show what the friction loss would be at 20, 25, and 30 gallons a minute. At this point, we'd have another parabolic looking graph started in our graph paper, and I'd consult my friend Norbit again and say, Norbit, what does that look like? And I think he'd come back and suggest that I should graph rather than pressure and flow. I should graph pressure and flow to the 1.85. And when I do that, I would get a straight line. Could run another series of tests where we replace the section of pipe with various lengths of pipe at constant flow. And I'll tell you, without actually dragging you through all of those tests, that curve would come out straight. And then once more, I could replace this section of pipe with various diameters of pipe. We get the same amount of flow, and when we measure the friction losses, we'd find out that it was related to the 4.87 power of the diameter, or the inverse of the diameter of the pipe. And there again, we could develop that Hazen and Williams formula. Those guys did that in the early 1900s, and it's been very useful ever since. The friction loss formula then just indicates that amount of friction loss varies by the length, varies by the flow, varies by the roughness, and varies by the internal diameter. Kind of the good news is, if you're doing a plumbing supply calculation, it uses the exact same formula. So Hazen and Williams did a nice job for both disciplines. Well, we'll remind ourselves now that we've talked about the pressure required at an operating outlet, and we've talked about the pressure required to overcome friction loss. I want to move to the last one of our physics formulas that relates what pressure is required to raise water to a given height. And once more, I'll skip to the punchline. And this is the simplest formula to write, and maybe the simplest to develop empirically. But The punchline is that the pressure due to elevation in PSI is equal to a constant 0.4331 times H, which is the height that you want to raise the water to in feet. We could do this empirical test pretty much with two items, a fishbowl and a weight scale. If we took a 1 by 1 by 1 cubic or a 1 cubic foot fishbowl and filled it with water and we weighed it, we'd find out that it weighs 62.3 pounds. If we measured the bottom of it, we'd see the bottom measured 144 square inches, 12 by 12. And then if we focused on 1 square inch a foot high, we'd say that was 63 divided by 144 pounds per square inch. And so that's equal to 0.4331 pounds. That's a 1 inch square, 1 foot tall. So 1 feet, the weight is 0.43, the square inches is 1, PSI is 0.4331. 2 feet is twice that, 3 feet is 3 times that. But if you always divide by H, then for any given height, it would be 0.4331 times however high it is, pounds per square inch. So our friction loss, or not our friction loss, but our elevation pressure formula then is P. The pressure required to raise water any given height is 0.4331 times the height. So we've got our three formulas. And this one, like the last, is exactly the same for fire protection and for plumbing. The advantage now is that this is pretty easy to memorize or keep track of. There's three formulas. First one is to get pressure out. Second one is to get the pressure up. Actually, the third one. And the second one is to get the water through. And so if we just remember, these are the formulas that are used to calculate the pressure to get the flow out. That's out the outlet, up the pipe, and through the pipe to get the flow out of the system. So that pretty much concludes our discussion of the physics of each of those formulas. I want to move very quickly to talking about the standards and codes applied to those designs. I've prepared a chart that shows both the fire protection standards and codes compared to the plumbing standards and codes, and I've indicated that we can consider that on a national, and an insurance, and on a local level. For fire protection, the NFPA 13 is the standard that is most used. It's part of the NFPA standards. NFPA 13 covers some of the most basic requirements, spacing of sprinklers, the density area requirements that are used to determine the total amount of flow out of a system, the special requirements for storage, and the actual procedures and printouts. Besides NFPA 13, there are other specialized standards within the NFPA standards that relate to some of these other particular instances of design: single-family dwellings, residential up to 4 stories, standpipes, fixed water supply systems, and stationary fire pumps. All of those, including the rest of the NFPA standards, are available for free viewing online at the URL shown there, or you can just simply Google NFPA 13 online. Besides the NFPA standards, Factory Mutual, or FM Global, publishes data sheets. Those data sheets generally provide even higher requirements than the NFPA standards. And as a preferred risk insurance company, those additional standards provide for better insurance rates. Those data sheets are also available for free viewing at this URL. By comparison, the plumbing codes are many and varied, but the UPC and the IPC, the Uniform Plumbing Code and the International Plumbing Code, are among the most popular and most widely used standards. They specify fixture units, conversions for those fixture units, velocity limits, and suggest report formats for the calculation of plumbing supply systems. the International Plumbing Code has essentially the same information, slightly different values, and in a slightly different format. I wasn't able to find those for free viewing anywhere, but they're available through Amazon.com and obviously many other outlets. And in both cases, local codes are very important in that they supersede often or augment the other standards. I'm going to move also to talking about the assumptions and talk first about the engineering assumptions applied to the plumbing systems. Within the plumbing calculation of a supply system, we start by assuming that not all fixtures will operate at the same time, and that those that do operate will operate evenly around the entire system. Further, the more fixtures there are in the system, the less likely it is that all of them will operate simultaneously. We also have to assume that we don't know when somebody opens a faucet just how far they're going to open it, so we have to pick an arbitrarily assigned fixed flow for each fixture that opens. The predicted flow and pressure at the supply point must be continuously available. We don't want it to work just for the first hour of the day, but for the entire day, all day, every day of the year. And it's also useful then only to exactly predict the approximate flow and pressure required for the supply, because of that varied operation of each of the fixtures. The reality lets you do it one way, but the engineering assumption gives us a better way of approximating that. And then finally, we limit the fluid velocities to improve quiet operation. So there are velocity limits in the plumbing design that are not in the sprinkler design. When we go to apply those assumptions to the actual analysis, we start by recording the fixture units for each fixture in the system. We accumulate those fixtures along each branch of the system, then use the tables in those IPC and UPC standards to convert the accumulated flows into actual flow rates. We apply the velocity limits to sizing the pipes. And then finally, we sum the outlet pressure, the friction loss, and the elevation along a critical path. This allows us to know the total flow rate for an entire building before we even start to size the pipe, because it's fixed by those fixtures. And often the sizing of the pipe is not based on friction loss so much as it is on the velocities. So by comparison, let's consider the basic assumptions applied to a fire protection analysis. First, we consider a single fire event will begin at a specific location, not randomly distributed across the entire building, but a single event at a specific location. For instance, someone puts a lighted match in a garbage can. The trash can catches on fire, and the fire grows from there. So the next assumption is that the fire will grow from that point of origin until the sprinkler system controls it. Just the actual ignition of the trash can won't set off the sprinkler. It's got to grow to a sufficient amount before the sprinkler system actually engages. The fire is controlled by the application of the required density of flow by each sprinkler within the area of operation. So that sprinkler system requires first the activation of its components, and that's generated by the fire growing larger and larger until sprinklers actually start to operate. Next, the sprinkler system must control the fire until the fire service can finish the job. So it doesn't have to operate all day long every day. It's just when there's a fire, and only until the fire department shows up and actually puts the fire out. This is pretty key, that our design basis or our assumption is that we're trying to control the fire. We're not really generally, we're not trying to put the fire out. Simply control it long enough for the fire department to show up. Next, the fire system must be designed to control that single fire event regardless of its point of origin. We don't just want it to work if it happens in the most favorable place in the building. We want, no matter what place the fire decides to start, that the system is designed to control that fire. And last on this list is that for any given event, we will accurately predict exactly the flow and exactly the pressure required of the system to control that fire. So given a specific location where the fire started, we'll know an exact area to operate, and we can determine the exact pressure and the exact flow for that operation of the system. I said lastly, but just as sort of an afterthought, there is no requirement for quiet operation. That's a comparison to the plumbing system that's operating all day long with people around. We'd like it to be quiet. Once the fire begins, there's fire alarms and a general alarm that people want to get out of the building. And if there's some noise associated with the operation of the sprinkler system, as I've mentioned before, that's not really a bad thing. So if we take these assumptions, we can put them in terms of the actual procedure that we would use to perform this analysis. We'd start by determining the density and area requirements for the type of building and the type of occupancy that we have. Those density and area requirements are specified by the standards. Next, we'd evaluate possible hydraulically remote areas. We want to go figure out what would challenge our system the worst. What's the worst place in the building that would challenge our system the most, so that we can analyze that area or those areas. For those locations, we would then measure out the area of operation. A typical density area requirement is perhaps 0.15 over 1,500 square feet. So given a challenge to our system, we'd measure out 1,500 square feet in step 3. In step 4, we'd measure out the area covered by each of the sprinklers within that 1,500 square feet. That area would be used in step 5 to calculate the required flow out of that particular sprinkler, out of each of the sprinklers within that area. Each sprinkler would require a flow of the required density times the area of coverage of that sprinkler. Once we know the flow and we know the K factor for the sprinkler, we would be able to determine the pressure at that point. And we use that outlet formula, which was the first of the formulas that we discussed at the very beginning of this presentation, to figure that pressure. With that as the starting point, we would repeatedly apply step 6, where we follow a path from the most remote head all the way back to the supply point. And for each pipe along that path, we would use the pressure at the pipe start to calculate the flow from any sprinkler at that point. We would then add that sprinkler flow to whatever the flow was in the previous pipe. Then we would have the total flow flowing through that pipe, and we could use the diameter, the length, that total flow, and the roughness to calculate the friction loss in that pipe. We would also include any elevation differences between the pipe ends to calculate that elevation pressure requirement. And then we would be able to calculate the pressure at the other end of that pipe by simply summing the pressure at the beginning end plus the elevation pressure plus the friction loss to give us the pressure at the next end of the pipe. We would then subsequently follow to the next pipe, basically using that same procedure in step 6 over and over and over until we got back to the supply point, where we would then know the total pressure and the total flow exactly that it would take to operate all of those sprinklers in that remote area. To be more specific, let's take a sample sprinkler system and apply that procedure. Okay, so let's take all that we've learned and apply it to a very specific sample sprinkler system. So we're going to run through that analysis procedure on this example. The building we're looking at is a 3-story classroom building. You may even recognize it as one of the tutorial samples in the Revit MEP program. We're going to describe a sprinkler system that has a standpipe that takes water from the city supply and feeds it through a standpipe in the corner stairwell. Then we're going to use 3-inch cross mains through the hallway of the classroom building to feed water into the classrooms. The classrooms themselves will have branch lines connecting the sprinklers within the classrooms, and then those branch lines will be connected back into the feed main with a 3-inch cross main, from each set of branch lines. So that's our sample sprinkler system. Step one of our procedure was to determine the density and area requirements, and if we consult NFPA 13, Chapter 11, we can find that for a light hazard classroom type of application, the required density is 0.1 gallons per minute per square foot over each one and every one of the 1,500 square feet of the most remote area. There are actually some deductions that you can take for elevation and flatness of the ceiling, but in this example, we're going to go ahead and use the 1,500 square feet. Then we're going to, in step two of our procedure, evaluate possible locations for that hydraulically most remote area. I'm going to give you two possibilities here and some thoughts about each of those two possibilities. Almost every reviewing authority wants to see a calculation of the physically furthest away remote area. This 1,500 square feet has an outlet pressure based on 225 square foot spacing of the sprinklers. It has an elevation pressure necessary to raise water up to the third floor, and it has friction loss necessary to carry flow for 8 heads through the longest path from the standpipe. By comparison, if we took into account another potential area in the upper middle of the building, that has an outlet pressure less than the one we just talked about, because all of the heads are spaced at something less than 150 square feet, and so that outlet pressure would be the minimum of 7 pounds. The elevation pressure would be the same because we're still raising the water up to the third floor. However, the friction loss would be required to carry water for as many as 16 heads, or in this case exactly 16 heads, through what turns out to be the shortest path from the operating sprinklers back to the supply. The outlet pressure in this case is less than the first one we considered, the elevation the same, but this friction loss based on 16 heads could potentially be more than the friction loss for that longer path. The additional flow for 16 heads causes a greater friction loss. In fact, all other things being equal, 16 heads would have almost 4 times as much friction loss as 8 heads. It may be that the path is about 4 times longer, and that might even them out. Still, each area should be considered in terms of these 3 ingredients to the total pressure required, what it takes to get out, up, and through. For the remainder of the example here, we're going to focus on that first area. Ultimately, both would have to be done and compared. So I'm going to measure out the actual area of operation in that lower right-hand corner. So let's zoom in a little bit and focus on that. In measuring out that area, we're going to figure 1,500 square feet. Theoretically, 1,500 square feet would be 30 by 50, or in this case, 32 by 46 and a half feet. The area needs to be, by NFPA 13 requirements, at least 1.2 times the square root of 1,500, or 15 square root of the area, long in the direction of the branch lines. But even though this area is exactly 1,500 square feet, you can see the yellow shading cuts halfway through the sprinklers on the top line and sort of partway through the sprinklers down the left-hand side. And the fire is not smart enough to partially operate a sprinkler, so we need to stretch and fit this area so that it actually covers fully operating sprinklers. And now the area is still longer than 1.2 times the square root of 1,500, and for these 8 totally operating sprinklers, the total area comes out a little more than 1,500, 1,550. Very good. So that shows the remote area that we're going to calculate and the 8 sprinklers operating within that area. Next, we're going to measure out the operating area of each individual sprinkler. If we focus on the furthest to the right and the furthest south in this picture, the distance between branch lines for that sprinkler is 15 feet. The distance between heads along branch lines is 15 feet. And so the area covered by that furthest, most remote sprinkler would be 15 times 15, or 225 square feet. his three nearest neighbors are also 15 by 15 or 225 square feet. And then the next four neighbors to the left of that are not as spaced as far apart, only 10 feet in one direction and 15 in the other, so that those are required to get enough water for 150 square feet each. Step 5 of our procedure was to calculate the flow at the most remote sprinkler based on the formula Q equals the density times the area. Remember, the density was 0.1, and the area for that worst sprinkler is 225. So that gives us the density times the area is 0.1 times 225, or 22.5 gallons per minute. The outlet formula that we developed right at the beginning of this presentation was Q equals K squared of P. We already know the Q, that's 22.5. We already know the K, that's 5.6. So we can rewrite that equation to get the pressure as the flow divided by the K factor squared. Substituting 22.5 and 5.6 and squaring it, we get a starting pressure of 16.14 psi at that furthest sprinkler. Next thing we're going to do is transfer some of that information to some actual calculation sheets. Here's one of those calculation sheets as prescribed in NFPA 13. And we're going to take and record or annotate that first starting point as reference point 1. We're going to record the flow added at reference point 1 of 22.5. And then we're going to record the K factor of 5.6. and the starting pressure that we just calculated of 16.143. Since there's no other flow added at that point, then the flow through this first piece of pipe, starting at reference point 1, the total flow is 22.5 also. So we can record that on the calculation format. All right, then, on to step 6. And this is the step that repeats itself over and over, following a path from the remote head to the supply point for each pipe along that path. Part 1 of step 6 is use the pressure at the pipe start point to calculate the flow from any sprinkler. For the very first point, this is exactly step 5, which we've already done. So we've already filled in the K factor, the flow added for the sprinkler, and the pressure at that first head. We're working on the pipe from 1 to 2. That's that very first pipe in the whole sequence. And as a result, we'll make note of that in our form also. So we're going to calculate the pressure for the friction loss between point 1 and point 2. We're going to record the length and the flow and the C factor and the diameter, both on the form and in our formula. So we'll start by filling in on the form that we're going from point 1 to point 2. And then we'll write in the diameter into our form, both the nominal and the actual internal diameter, and note that on our formula. Then we'll make note of the length as 15 feet, and we'll mark that on our form and on our formula. And then we'll take the accumulated flow, which on this first pipe is the same as the flow out of the sprinkler, the 22.5. Note that on our form and highlight that in our formula. And then we'll get the C factor, in this case 120, for the roughness for that pipe. And then we've got all the variables filled in for that formula, so we can calculate the friction loss per foot times the number of feet to get the friction loss in this particular piece of pipe. So the friction loss point for the friction loss per foot is 0.1618, and the total friction loss in this segment of pipe between 1 and 2 is 2.427, and we've written them on our form. The next section of step 6 then is to use the elevation difference between the two ends of the pipe to calculate the elevation pressure between the two ends. End 1 is at 33 feet, end 2 is at 33 feet, and so the formula is 0.4331 times the height difference, in this case 0, and so the elevation pressure required is 0, and we write that on our form and show it in the formula. And then finally, we're going to calculate the pressure at the other end of reference of the pipe from 1 to 2. And so the pressure at point 2 is the pressure at point 1 plus the elevation difference plus the friction loss. So the pressure at point 1 was 16.143. The elevation pressure was 0, and the friction loss was 2.427. So we add those all together and we get 18.57, which is the pressure at point 2. So that was step 6, and we just repeat step 6 for the next pipe, because we're going to do it for every pipe in that path. So the pipe from 2 to 3 starts out with the results that we got from pipe 1 to 2. So we add the sprinkler flow to the previous pipe. So the flow at this reference point 2 was 24.13. The added flow, 24.13, added to the flow in the previous pipe, 22.5, gives us the 46.63. We use the diameter, the length, and that 46.63 gallons per minute to calculate the friction loss. We record all of that on our form. We use the elevation difference, again 33 at both ends, giving us an elevation change of 0. And then we can calculate the pressure at reference point 3, the other end of this pipe, by adding the starting pressure of 1857 plus 0 plus 2.131 to get 20.707. We'll just follow that pipe by pipe by pipe all the way back to the supply. And along that path, there's a few things we have to keep in mind. The flow from any sprinkler at that point has to meet the minimum, and if not, then we need to raise the pressure at the beginning point in order to get the minimum at a given point. In this particular calculation, that wasn't necessary. It was always enough. We also have to get the flow from any branch of piping that can be added at the same pressure, and if not, we can recalculate the flow required from that branch until that pressure balance is within 0.5. We calculated branch line 1, and when we got to branch line 2, we didn't quite have the same pressure and flow, and we just calculated branch line 2 until the pressure was the same as branch line 1 plus a little piece of the cross main. Also, not required of this particular calculation, but one other consideration is that the flow from any alternate route of piping in a looped or gridded system can be added at the same pressure at any given point. But if they're not at the same, then you can recalculate by dividing the flow in an alternate manner so that the pressure is balanced within a half a pound. So on a looped-in gridded system, that can get a little bit involved. So following that through pipe by pipe by pipe till we get all the way back to the supply, I've just highlighted the last few pipes in this calculation, the last couple, and showed here that at reference point test, back where the supply of water comes into our system, we needed 299.75 gallons per minute for the entire system, including 100 gallons a minute for hose, and we needed 62.81 pounds of pressure to deliver that almost 300 gallons a minute. This comes from the HydroCalc program, which can automatically do the set of calculations for us. And since there's many pipes along that path, it serves to summarize it by pretty much taking care of all three of those formulas in a summary: the out, the up, and the through. And on this little bar chart, the black section on the left is the out. That's that 16.14 pounds that we needed at the most remote head. The light blue, the yellow, and the dark blue are the through. Those are the friction losses to get the water through the branch lines. That's the light blue of about 17 pounds. The yellow, which is the mains, about 14 pounds. The underground and the riser piping was very little, 0.5 pounds. And then The up is the elevation pressure of 14.23. By summarizing it this way, it helps bring into focus the idea that it's those three components, the out, the up, and the through. The brown bar on this chart on the right is the pressure available out in the street, and we always want the left bar to be shorter by some amount than the bar on the right, so that what we need is less than what we have available. So I want to take a minute and go back and reconsider the design for comparison purposes. The design that we started with had 4 heads at 225 square feet and 4 heads at 150 square feet. So we had to calculate 8 heads worth of flow through the whole rest of our system. If we were to add 2 sprinklers, so that our most remote area was 10 heads, and recalculate the system, some interesting things would happen. And let me skip to the sort of the punchline here. This is the end of that calculation, where it shows the total required flow was 259 or 269.74 gallons per minute, and the pressure, the total pressure, was 44.069. If you remember from a slide or two ago, that was 299 more flow and was 62.81 more pressure. And so adding 2 heads decreased the pressure and flow. That's a little counterintuitive, but the basic reason for it is that the heads were evenly spaced, so we got closer to the minimum amount of flow that we needed, and we started with a smaller end head pressure. Here's the bar graph summary of the calculation that we did, and you see the end head pressure is 7 instead of 16, and the line and main loss are both less because the total extra flow required was less. So here's those 2 bars next to each other. The 8 head calculation needed 63.9 pounds, and the 10 head calculation needed a total of 44 pounds. So, like I say, it's a little bit counterintuitive, and I threw that in as a twist to kind of get you thinking. You have to always think about the out, the up, and the through, and the total combination of those dictates the total flow and total pressure required for a given system. Well, now that we've been through a very detailed analysis or procedure to show you the fire protection calculations, I just want to come back to the original assumption of comparing fire protection and plumbing systems. I've prepared a chart here that shows the key differences: the outlet pressure, the friction loss, and the total system flow. In the fire protection system, the outlet pressure varies by which area you're analyzing, and it uses different formulas from the plumbing system, where the entire system can be determined just by the type of fixture that you're using, and the flow then is a constant by that fixture type. For the friction loss, we're using the exact same formula in both approaches, fire protection and plumbing, but the flow through any given pipe in a system is dependent on the downstream flow in that system and varies by which area you're assuming is operating. In the plumbing system, where you assume the entire thing is operating evenly distributed, you can much more easily determine the pipe diameters, which are chosen by velocities, and the fixed flow of all the downstream fixtures. And then the total system flow varies by what it is you're analyzing in the fire protection, whereas it's way more straightforward in the plumbing system, where it's a constant for a given set of fixtures, meaning it's constant for that building. Well, we've been through that overall series of topics that we wanted to discuss: the physics of each of the formulas, the standards and codes, and the important assumptions in applying those formulas, and made that comparison between the fire protection and the plumbing system. So we've covered a lot of information in what I hope seemed like a short period of time. I'd like to thank you for your interest and your attention. I'd also like to remind you that there is more information available on the handouts and that you can download those and study them at your leisure. I'd also like to encourage you to fill out your evaluation forms. It's that information that I'll use for any future considerations for presentations. And lastly, if you have any questions, my contact information is to the right. And again, you've got provision through AU in this virtual environment to make those questions known, and I'll get back to you through that process. Thanks once more, and enjoy the rest of your AU.